Recording in progress.
Okay, good morning, everyone. Today we're going to start like a new phase of digital logic. So far now you have all the tools that you need to build any digital circuit. Okay, so now we're going to be starting how to use those tools, and we'll get to know a little bit about the basic elements that can be created or built using for any microprocessor. Okay, so starting from a very simple microprocessor, like for a calculator, for example, all the way to the microprocessors that we see in our computers. These are all based on some common digital logic circuits we're going to learn about this semester. Okay, so you're going to have like those basic blocks that can build a microprocessor, and then when you go to the next sequel of digital logic, you're going to put these things together, get to, into more advanced stuff. Okay, so as a recall, from last time we started, we talked about all the numbering systems that we've learned about: the decimal, the hex, the binary. How can we transfer or convert from one decimal numbering system to the other? And we talked also about binary numbers, signed and unsigned, and this is crucial when we start to talk about adders and subtractors, like the one that you see in your calculator, for example. So we're going to be building those, and we really need to be aware of which is signed or unsigned. We've learned how to add those two signed numbers or unsigned numbers, or how to subtract them. And in the subtraction, what did we use? We used the two's complement. Okay, and two's complement is going to play a big role today, okay, in our system designs. So the main objectives of this chapter is that we're going to be designing the common digital arithmetic operation circuits that are used to build any microprocessor. So we're going to get to know what is that, how to build an adder, how to build a subtractor. We're going to learn what is a multiplexer, encoders, decoders, and comparators. Okay, we're not going to finish all of those today, but we're going to take only the first half. Okay. So now let's talk about the adder. Okay. We've learned about how to add two binary numbers, right? So let's add two binary numbers together. I have the A and the B. Let me just change the color. I have the A and the B. And I would like to add these two numbers. I will always have a summation, and I will always have a carry out. Remember, we will always have a carry out. Okay, so let's start with the first one. So let's go to this table here so we can start to wake up. 0 plus 0, A plus B, 0 plus 0. What is your summation? What's your carry out? 0 and 0. Okay, now let's move on to this, and we're going to rechange, okay, so that we can have 3 in table. So let's go to this table here. What is 0 plus 1? The sum is 1, and the carry out is? No, the carry out. Are you taking any carry out to the next position? No, so the carry out is going to be a 0. Okay. Now for 1 plus 0, Dan? No, 1 plus 0. Yeah, it's just 1, and your carry out is just a 0. Okay. Now for 1 plus 1, let's go back there somewhere. Excellent. So the summation is going to be a 0, and the carryover is going to be a 1. Okay. Now we want, from these two output lines, we want to build what we call a half adder. We're going to learn, okay, why did we call it a half adder, and how can I fix that, because it's not going to really work for our calculators or microprocessors. So first, to find the summation, we're going to look at where the outputs are equal to 1, okay, and then find the minterms for those two, add them together. So let's do that. So if I say that the summation is equal to the first minterm here, Alejandro, first minterm here is going to be what? A complement, B, and the second one? A, B complement. Can someone tell me what is that circuit? The XOR. So that is exactly the A XOR the B. So that means that to build the part of the summation, I just need to have an XOR here. One is connected to the A, the other is connected to the B. Just switch those two since I put it here. So this is going to be your sum. Okay, so your summation between the A and B by using an XOR gate. Okay, what about the carry out? Jose, what about the carry out? What is the midterm for that? It's only one midterm, AB. So your carry out is just A ANDed with B. So that means that I'm just going to have an AND circuit here. Going to connect the B and connect the A. Okay. Now, we need to think a little bit. Here, I'm adding only a single bit plus a single bit, right? Now, my question is, what if I want to add a 4-bit plus a 4-bit or an 8-bit plus an 8-bit, right? This is not really going to work, right? So for example here, if I have A and my A is equal to 0, 0, 1, 1, 1, so these are 5 bits, and I want to add it to B that is equal to 1, 0, 1, 0, 1, okay? Now, let's think together. What are the options that I can do to create, knowing that half adder, that block that can only take 2 bits, add them together? What are the options that we can do? This is brainstorming now, okay? Okay, good. So I can put 3. Why don't you put 3? Why don't you put 5? So you want to add the first one to the second one that needs a half adder, right? The second 2 numbers need a half adder. So probably we can put 5, right? Okay. So if this is your half adder, and these are the 2 numbers you want to add, let's start to have 1 half adder for this one half adder for this one, for this one, for this one. Okay, my next question, will that work? It should work, right? Okay, now let's see how it works and what is the problem with it. Okay, so that it can take us to the next design. When I say 1 plus 1, 1 plus 1 is going to be what? 0, and you carry over a 1, right? That's the carry out. Okay, 1 plus 0 is a 1, and the carry is a 0. Okay, now 1 plus 1 again is a 0, carry out is a 1. 0 plus 0 is a 0 with the carry 0. 0 plus 1 is a 1 with a carry 0. Okay, so this is your summation, which is the 0, the 1, the 0, the 0, the 1. So it is 1, 0, 0, 1, 0. Now, is that really, when we add these 2 numbers, is this going to be the result? Now, what is the main problem with this design? Excellent. I had the carry over, but I didn't take it to the next position, right? So it means that I'm just adding the 1 plus 0, but there was a 1 from the previous position that was needed to add to that one. So the results here are not right because I'm not using the carry out. So if I want to use the carry out, it means that for some reason or for somehow, and instead of having the A and B in every input here, I need to have a third one. I call it the carry in, just in case I have a carry in from the previous position. Do we all agree? So to solve this problem, and instead of designing what we call a half adder, we're going to be designing what we call a full adder. Now, how does it work? See, we have here these 2 numbers. You have your summation, 1 plus 1 is a 0. You carry over the 1 to the next position. Now, how many inputs do you have? 3. One of them is the A, one is the B, the third one is what? Is your carry in. Okay, so my mind has to think about, okay, if I want to design another adder, I should have 3 inputs, not 2, right? One of them is the A, the other is the B. The third one is going to be the carry input in case that I have it. And that turns to create what we call the full adder. Okay, and that's the one you're going to be designing in your lab this week. Okay, we're going to be designing the full adder. So for the full adder, it will add 3 bits. Okay, now we know where are the 3 bits. 2 of them is from the 2 main numbers we want to add together. The third one is the carry input in case that I have it. Now let's address all the different possibilities that can happen when we're adding 2 numbers plus a carry in. And let's see what is the sum and the carry output. We're going to use Boolean algebra, not K-map. We're going to use Boolean algebra rules to find the expression. And then we're going to find the relationship between the full adder and the half adder. Now you're going to shuffle around at least 3 per table, and we're going to start to work on filling up those truth table and try to come up with the expression. I'm going to walk around. 3 per table, please. Alicia, Alejandro, Alex, Andrew, Anthony, Brendan, Dan, Danielle, Daryl, there, Data, Ethan, Ezekiel, Gunnar, Hugo, Isaac, Isabella, Ivan, Jack, Jake, David, Jesse, Jose Loya, and Jose Magdalenas, Ryan, Stephen, Summer, each row is independent. Don't carry from first row to second row. You're just having, if you have 0 plus 0 plus 0, what is your sum? What's your carry out? Each row is independent. Because I was hearing some kind of, each row is independent. Good. Okay, the last one. Check the last one. You said 1 plus 1 plus 1 is what? 1 and 1. Yes. Okay. Now look at the midterms. Extract the midterms. Now try to find the midterm. Are you guys done? The midterms. Now, for the summation, look where all the inputs are equal to 1. I want you to write down the expression. I will call out a certain table to tell me what's the midterms.
We want the sum of midterms?
Yes, I want the sum of midterms for the sum and for the carry out. You're gonna look where it's equal to 1, you're gonna add those together. And then we're gonna minimize it together, simplify it together. So most of you got it right here. So you're going to have 4 midterms that needs to be added together. Okay, so let's start with this table back again. Ethan, can you tell me the first midterm?
A naught, B naught, C N.
C, good. I'm just gonna say C just for short. Okay, Jake or Jack?
A naught, B, C naught.
A naught, B, C naught, good.
A, B naught,
A, B naught, C naught, Alejandro?
B, B, C.
A, B, C. Okay, now next we want to simplify this, and I want you to pay very good attention when I'm simplifying it, because we want to relate it to the half adder. Okay, when you're learning in VHDL, you're going to learn that I can do a small block and create a bigger block out of it and just use it as many times as I want. So for example, when you are building in your lab an 8-bit plus an 8-bit, you don't have to build 8 full adders and make 8 codes. You're going to create only 1 code, and then you're going to just use it with the port map. Okay, and you're going to see that very clear on Thursday when we talk about it in class and in the lab. But just keep in mind here is that we want to relate the full adder and the half adder somehow. So that's why I'm using here Boolean algebra. I'm not going to be using K-map. Now, let's take these 2 together. If we take these 2 together, what do we have in common? The A complement. So I'm going to have B complement C plus BC complement. Okay. Now for these 2, I'm going to take the A as a common factor. I'm going to have B complement C complement plus BC. Now, let's pay attention to the next step. I will assume that this is, I'm just going to give it a new name. Okay. I will assume that this is, for example, X. Okay. So I'm going to say that my X is equal to B complement C or BC complement. What did we say the circuit is? This is an XOR. Remember, this is an XOR. The B XOR C is the B complement C plus BC complement. Okay. Now, if I want to take the complement of the X, okay, it means that I'm going to take this whole thing and I have to put a big bar on top of it. So how are we going to be breaking this bar? De Morgan theorem. So I'm going to change every and to an or, every or to an and. Okay, and because I want to keep the first 2 together and the second 2 together, we're going to put parentheses. I have B complement C, BC complement. Don't forget to break this big bar on top of all. Okay, so now you have what? B or C complement ANDed with B complement or C. Now let's do the distribution. So you're going to have B ANDed with B complement. B ANDed with B complement is what? 1, 0. What about 2? B ANDed with B complement. The AND. Remember, AND like multiplication. So it's going to be 0. So B ANDed with B complement is a 0. Okay. Now B with a C is just going to be BC. B complement, C complement. And then C complement ANDed with a C is another 0. So actually, we can just take this 0 away. So this is what I have. Now, anyone tell me what is this circuit? XNOR. Excellent. This is the XNOR. And we've learned the relationship between the XOR and the XNOR. What is the relationship between XOR and XNOR? Inverse of each other or complementing to each other. So that means that if this is my X, okay, my X complement is just the B XOR C complement, or in other words, it's the B XNOR C, right? Do we all agree on that? Okay, now we're going to go back to the summation. So I'm going to say that the summation is A complement X. I'm just going to put now that whole parentheses as an X plus A X complement. Now I know that the X complement is going to lead to this input here. Now, what is this in itself? Again, the A and the X, the relationship is an XOR. So this means that this is A XOR X. Now, if I want to erase the X and substitute it with its value, it's gonna be what? B XOR C. So in other words, it's telling you that when I am adding A plus B plus the carry input, I'm just gonna pass those three to an XOR gate, and it will give me the sum, not the carry out, the sum. Is that clear?
There's no parentheses needed here to.
No parentheses, no. It's just A XOR B XOR C. Any questions? How did we get this? You're gonna redo this in your lab again, by the way, in the pre-lab. Do you understand it? And it's not in the Zai book. Is it clear? Okay. Now, let's do the carry out, and then we're going to do an observation on the full adder and the half adder and try to come up with a relationship between them. So we finished the sum. Now let's do the carry out. So how many inputs do I have for the carry out? I have 4. So let's move to this table here. Can you tell me the first minterm? A naught, B, C. Thank you. Next. Stephen? Mm-hmm. Okay. Jose? A, B, C naught, and finally, Evan? A, B, C. Good. Okay. So for this one, we also need to do the same thing. We need to come up with using Boolean algebra, and we need to come up with an expression. Okay. So I'll just give you like half a minute to think about, because this one is a little bit easier from the first one. And I want you to come up with an expression by taking the first 2 together and taking the second 2 together. If you can get it, raise your hand. I want you to take the first 2 together and the second 2 together. I know there's many other ways, but this is how we want to do it. Anyone? Okay.
For the first one, I did C.
Mhm.
A naught, B naught, plus
A naught, B naught, or A naught, B?
I
Yeah.
switched around.
Okay.
A naught, B and A and B naught.
And A, B naught. Good. Okay. And for the second one?
A, B.
A, B as a common factor.
B naught plus.
C. Good. Okay. Now, what is C naught or with a C? 1. Okay, good. Now, what is A complement B plus AB complement? What is the circuit? We've seen it a lot, XOR. So I can say that this is equal to C, and of course C is related to the C input, A XOR B plus AB. That is your carry out. Okay, and this is your summation. Now, any problem trying to derive those 2? Clear? Okay. So now my summation for the half adder, and I'm just going to put a subscript HA, that means the half adder. If you take a look in your notes, you're going to notice that we found that the summation for the half adder was A XOR B. The carry output for the half adder was A and B. And this is the circuit that we came up with. Okay. Now for the full adder, the summation was A XOR B XOR C input. And your carry output was AB plus C input A XOR B. Now I want you to look carefully at these 2 and tell me what is the relationship between the full adder and the half adder in terms of the expression. So this is like the full adder. Look at the equations. Don't look at the schematic. Look at the, what do you see there? Just raise your hand and give me a thought, okay? Yes,
I'm saying it's like, see how it's like, bring down the AB, see out from the half adder and add it with the CN and we just multiply it with the sum,
of the,
half adder.
excellent, okay? So for example here, for the carry output, here, I can say that the carry output of the full adder is equal to, what is A and B? A and B is the carry output for the half adder, plus I have a carry input. Now, what is A XOR B? A XOR B is just the summation of the half adder. Right? Now I'm relating the full to the half. So it means that if I build the half adder only, I can just use this expression and create a full adder out of it. Okay, I don't have to create the full adder from scratch, or I can just create the full adder from scratch. So in class, in lab, you're going to be doing both ways. You're going to see how you do both ways. Okay. Now, can someone tell me the relationship in the summation? So you did the carry out. What about this one, the summation? I need someone else. Yes, Ethan.
It's the sum of the half adder XOR with C.
Excellent. So the sum of the full adder is just the sum of the half adder XORed with the C input. So you see that this is your full adder. This part is the summation of the half adder. This part is the summation of the the carry output of the half adder. Okay, I combine these together with an extra XOR, and here with an extra and an OR, and then I created the full adder. Now, do you see how did we create that? Now this one can solve the problem if I have 5 bits plus 5 bits, 8 bits plus 8 bits, whatever number of bits I want to add them together. Now I guarantee that I'm adding the two numbers. There is a carry over from the previous position. I have a spot for that. So back here to these two numbers, if we want to add these two numbers, now what are we going to be doing? And instead of putting a half adder for each one of them, we will put a full adder. So this is my first one, second, third, fourth, and fifth. So it means that if I have a 5-bit number plus a 5-bit number, I need 5 of those. If I have 8, I need 8 of those. Okay. Now let's go one by one and see what's going on here. I have 1 plus 1. So my A is the 1, B is the 1. What is your carry input? Is a 0. So always the first carry input is always going to be a 0. Pay attention to this point, because when we try to design a full adder and a subtractor together, we're going to use this piece of information. So the C input for the first one is going to be a 0 because I have nothing coming before. I'm just starting to add the two numbers. So the C input here is always a 0. Okay. Now I added A plus B. So the summation is going to be 1. It's going to be 0. The carryover is going to be what? 1. Now that carry out is going to be the carry into the next position. So you're going to have a wire connecting the carry out of the first one to the second one. Now we're having 1 plus 0 plus 1. Okay, so 1 plus 0 plus 1 is going to 0 and carry over a 1. Now you take that 1 to the next position here. So you're going to have 1 plus 1 plus 1 is going to give you 1 and 1. You take this to the next position here. Oh, sorry, here to the carry input. So you're going to have 1 plus 0 plus 0. Summation is 1. Carry output is a 0. You carry that 0 here. You have 0 plus 1 plus 0. It's just going to give you a 1. Carry output is 0. So now where's your number? These are the summation. That is creating your number, which is 0, 0, 1, 1, 1. Now, we consider the last carry output as part of the number. Why? Because I can add 5 bits plus 5 bits and end up having the 6 bit. So always the carry output is going to be your 6th bit. Okay, and we call that overflow. Also, you're gonna see that actually in your lab. So we're gonna have the 0 here, and that 0 is for the carry output. Okay. Clear? Good. So now we're going to think as an engineer who wants to design now something official. Now we had all the tools, but now we want to see how are we going to be designing this. So for example, here I have 4-bit plus 4-bit. Usually our adders are 4, 8, 16, okay, power of 2. So if I have 4 bits plus 4 bits, I'm going to assume that the 4 numbers, I'm not now putting 1 and zeros, I'm just going to say it in terms of A3, A2, A1, A0, because that's how you're going to write it down in your code. You're going to say, for example, standard logic Victor, okay, 3 down to 0, down to 0. And that is like, for example, that's your A. So your A is a Victor of 4 bits, okay? Your B is another Victor of 4 bits, okay? So I know that for every 2 single bits, I have to have a full adder that's going to add A0 plus B0 plus what? Plus 0 for the first one. And then here it's going to be A1 plus B1 plus anything that came out from here. If the carry out here has a number, like a 1 or a 0, I'm going to load it here, okay? And you keep going. Okay, so this is what we call a 4-bit full adder. Now, so this is telling me that if I want to design a 4-bit full adder, I'm going to have like A3, A2, A1, A0. So these are, think of these as your switches. Okay, you have 4 switches for the A, and then you have B3, B2, B1, B0. Okay, and again, you're going to have your first carry input, okay, that's also going to be a switch from the outside. But notice that the carry output here is an internal signal. So we don't really need to see from the outside because this one is going to be fed to the carry input here. This output is going to be fed to the carry input here. We only care about the last one, okay? So the last one, so for example, for the summation here, this is going to be on an LED. For example, this is going to, you're going to put on another LED, and this one is going to be on the last LED. So if we have here LED of 1, this is going to be of 2, 3, and this one is going to be of 4. Okay. And as we said, because we're adding 4 plus 4, we can end up having 5 bits. So that's why we have the carry out. And we call that an overflow happen. Okay. So this is how, like we have the IC build, but this is for the other classes. They build it hands-on. The IC chip already have built in 4 full adders inside it, so that it can allow you to add 2 numbers. Each one of them is 4 bits. Your carry input here, that's the original carry input of the first position. You can, connect it to 0 or 1. And this is your 4 numbers of the summation, and that is your carry out. Okay. Now, usually you see here, this line, if I put a slash on it, it means that it is not a single wire. It is a wire of a size, and the size we put it here. So we're going to see that a lot. We have a /4/8. It means that these are 4-bit or 8-bit. Okay, it's like a bus. Now, it's not a single wire. It's a bus of 4 wires. Okay. Now, if I just want to create like a timer, okay, something that's just going to count down or count up, for example. So if I'm just creating a counter that's going to count up or down, I can just use a half adder. I don't need a full adder. Do you know why? Because I need only 1 number, and every time I'm going to be adding the number 1 to it. So I don't need a second number. So I can use the half adder. The A is going to be the number. The B is actually going to be that 1 that I'm going to be adding to the first digit. So I will here add a 1 to the first digit. That's for the half adder. I have a thumb, and I can take the carry over to be my next number in the half adder. So if I want to do just an increment, I can just create it using the half adder. I don't need a full adder because I'm not adding 2 numbers. It's only 1 number plus 1. Okay, now we've learned how to create an adder. What about a subtractor? Okay, your calculator has a lot of things in there, right? So to do a subtractor, which is A minus B, now we know that the borrowing kind of thing, in implementation, it is very difficult using the two's complement is very powerful in implementation. And we're going to see how powerful it is here. If numbers are representing, they're using the two's complement representation, I can use, the subtractor can be built using an adder. So actually, I don't have to build a subtractor. I just need to be creative and see how can I make use of the full adder with some knowledge about the two's complement and create a subtractor from an adder. Okay. So any thoughts? How can we do that? Let me give you two hints. Number one, what is the two's complement of the number B? We said that you scan until you hit the first one, but of course you're not going to do that in the design. Let's do the official way. So the official way is that I take the B, I complement it, and then add a 1. What do we mean by complementing a number? Is passing it through what? An inverter, okay? So the two's complement of the number is just the opposite of the number by adding a 1 to it. Now, I have a 4-bit full adder. These are adding two numbers. And now I'm asking you that I want to make a subtractor out of this adder. So I wanted to do A minus B and instead of A plus B. Now I'm going to give you 2 minutes, brainstorm. Okay, and if a group can come up with a solution, you will get extra credit. Think quickly. You have 2 minutes. This is how you're going to do outside. You're going to have a problem, you have some tools, and now you put things together to create something out of it. Just think together and then raise your hand, I can come to you. So we. You guys ready? You have an idea? Okay, okay, yeah, we're saying A minus B. We're gonna add the other plus one of this, okay? We're gonna get that one. Okay, anyone else came up with an idea? You guys came up with an idea? Okay, anyone else have any idea? Okay, let's see what you have here, and then our 2 minutes are over. No, I just wanted in terms of implementation, what are we gonna add in terms of surveys? Not equation. Okay, so let's take a look here. Let's pay attention. When I say A plus B, okay, I know that A plus B. Now, when I say A minus B, we say that I take the A as is, I turn this negative sign to a positive. Remember how we did it? We return the negative sign to a positive sign, and then I find the two's complement of the B. Now, I'm telling you that the two's complement of the B is just B complement plus 1. So it means that I need to add the A plus, not the B's, the B complement, and then plus an extra 1. So I will use the C input that is always 0. I will use it for my extra 1 that I need to add. And then what I will do, I will just add inverters to the B's to make all of them be complements. Okay. So I complemented all of them. I added a 1. Now I have a 2's complement. I added to the A. Actually, that's a subtraction operation. Clear? Good. Now, do you have a calculator for addition, another one for subtraction, one for multiplication, one for the trigonometric? Of course, it's one calculator doing all, multi-purpose. Now, this is what we're going to learn from now on until the end of the semester, is that as an engineer, you never do a design that does one job, okay? So saying that, it means that I have to think of a way to make one circuit that can add the adder and subtractor together in one circuit. I don't want to be built one for the adder and one for the subtractor. When I say, hey, add these two numbers, you go to this design, and then you go to this design for, no, I want them in one circuit. So how can I design one circuit that includes both addition and subtraction? Now, we used, probably in the lab, but we're going to get exposed to it today, the multiplexer. Remember the multiplexer? We learned how to write it down in multiple syntax in VHDL, but today we're going to talk about it a little bit in depth. So what is this? That's a vending machine. Okay. Now I want you to tell me step by step, what do you do? Number one, you look at the vending machine, right? To see what you want to choose. Now you had a decision that you maybe need a chips or a soda, whatever. Now, what is your next step? Okay, let's skip the money part. Let's say this is for free, okay? So what is your next step? Location, or let's talk a little bit digital and say we put the code, okay? So I will be putting the code for the number that I want, like 01 will get me a chips, 11 will get me a soda, and so on. Then, what is the last thing that happens? It vents out from here. Okay, now how many things do you get out from here? One at a time. So with every code, I am selecting one of the products that you see in the vending machine. Okay, now the multiplexer works the same way. And guess what? The multiplexer is very powerful because anytime you want to design a system that's doing multi-purpose things, you're always going to have a multiplexer that you're going to assign a code for every job, and then you have the certain jobs, and then you're going to assign the code. You want to choose this one to operate right now, or you want to choose the second one to operate. Okay, so multiplexer, keep in mind. So when we're doing counters, we're going to later on design counters, up counter, down counter, and then we're going to put them in one circuit. Okay, we want to reset our counter. Okay, or sometimes I want to load it at let it start at a certain point. I can put all of those in one circuit by using the multiplexer. So the multiplexers are very powerful because you have different parts, and then you're just having a selector that's going to select which one is going to operate now. Okay, so that takes us to what we call a multiplexer. So a multiplexer will always have multiple inputs and only one output. So think about this. This is your candy. This is your soda. This is your chips. And maybe this is your chocolate, whatever. Okay, so these are your data. We call those, these are my data of the multiplexer. Now, these two are the selector. So when it's 0, 0, I will pass a candy. If it's 0, 1, I will pass, for example, a soda. If it's 1, 0, I'll pass a chips and so on. So you have data at the door of the multiplexer. You have a selector that's going to decide which one of them will pass through to the output. Okay, now we're going to learn it a little bit theoretically. The different sizes of multiplexers has to follow this following rule, that the number of inputs is 2 to the power of n. So I cannot just say 5 inputs, 6 inputs. No, it has to be 2, 4, 8, 16. Now, based on the number of inputs, I can know how many selectors I need. Because if I have 4 inputs, it means that I have 4 different possibilities. I can get those with using 2 bits, right? So 2 is going to give you 0, 0, 0, 1, 1, 0, 1, 1. Now, if I have 8 different possibilities, I need 3 selectors. So then I have 0, 0, 0, 0, 0, 1, and I got that truth table of 8 different possibilities. Okay? If I have only 2, I need only one selector because it's either gonna choose between I0 or I1. Is that clear? So when I'm designing a multiplexer, I have to know that the multiplexer is just a combinational circuit that will pass one of multiple data here. So here the data is going to be ones and zeros. And I don't know which one I really want to pass. The selector is the brain, is going to tell you which one I needed to pass to the output. Okay. Now for the selectors, we said that for 2 to 1 multiplexer, I have only one selector. For 4 to 1 multiplexer, we have 2 selectors. For 8 to 1 multiplexer, we have 3. So can we come up with a rule here? If you have n to 1 multiplexer, what is the number of the selectors? It's len n. So let me just make this easier for you and just say this is 2 to the power of n. So if this is 2 to the power of n, this will be n, okay? And if this is n, this is just going to be len n. Okay. Clear? So if I'm giving you a multiplexer, it's always going to be 2 by 1, 4 by 1, 8 by 1, 16 by 1, okay? It's always the output is only one output. Remember, the vending machine can only give you one output at a time. Is that clear? Questions? Sure? Okay, now we have the multiplexer. We have the full adder. We have the converter. So, and we're going to think of how we can create the adder subtractor circuit. But before we go that, this is very important, okay? You're going to see it somewhere. Quiz or exam. So here, we want to go now to the mathematical part of this. This is telling you that I have a data here that is called I0, I1, information 1, information 2, information 3. Now, is it a 1 or a 0? I don't know, okay? So I'm saying that when I have my selector 0, 0, I want my output to be the I0. So I want to pass the I0 to the output. When it's 0, 1, I want to pass the I1. Here I want to pass the I2. Here I want to pass the I3. Now, if I'm asking you, we want to write down the Boolean function equation for the output. The first rule that you've learned is that I need to look where the output is equal to 1, right? Where is the output is equal to 1? You don't know, right? So we're going to assume that the I0, I1, I2, I3, since I don't know what it is, I'm just going to add all the 4 midterms in terms of the I0, I1, I2, I3. And when then one of them is equal to 0, it's just going to blow that midterm away. So let's see how we do that. So let's say y is equal to, what is this first midterm? S1 complement, S0 complement, and it with the I0. So I'm going to add it with the I0. If the I0 is a 1, that's a midterm I keep. If the I0 is a 0, that's a midterm that's going to go away. Okay. Now for the second one, it's going to be S1 complement, S0, I1, plus S1, S0 complement, I2, plus S1, S0, I3. Now, if I say that if my I0 is equal to I1, and both of these are equal to 0, my I2 and my I3 are equal to 1, and my selector S1, S0 is equal to 1, 0. What should be my output? Now think about it. These are the products that you're having. This is the selector of my vending machine, and I want to know what the output will come up. Okay. So first of all, I0 and I1 are equal to 0. It means that this midterm is going to blow away. This midterm is going to go away, right? So the only midterms are going to stay are these two. Now, which one I'm going to be selecting? Will I select the data of the I2 port or the data at the I3 port? Well, it's based on this selector. It's saying S1, S0 is equal to 1, 0. So 1, 0 will throw what? Give you the I2. So sometimes I will just give you the selector, okay? I will just give you the selector and ask you for the Y. What will be the output of the Y? Okay, so let me just read. Let's do this, like take this away. and say, if my selector is S1, S0, what should be my Y output? Think about it. If I select the code 1, 0, what my vending machine will give me? If you do here, if you try to substitute 1 and 0, this is going to be a 0. This one is going to be a 0. This one's going to be a 0. The only one that's going to be left, these two are going to be a 1. So the only thing that's left is the I2. Okay. Now, what is the I2? I can give it to you. I say, well, the I2 data was a 1 or was a 0. Then you can say that your Y is that 0 or 1. Okay. Is it clear? Huh? So how can we come up with the equation? And then if I'm giving you a selection, how can you come up with the output based on the different inputs that you have and based on the selection that I gave you? Always think about the vending machine example. Okay. Questions? Okay. So now you have everything you need. I want to now create an adder subtractor. I don't want to make two circuits individual. Okay, it's going to cost me a lot of money as a company. I want to, save money. So I'm going to give you a full adder here. I'm going to say, do something. Okay, you can add multiplexers if you want. You can add inverters if you want. Choose your C input to do whatever you want. Think of how can I create an adder subtractor out of this circuit. So like 2 more minutes or 3 minutes. This needs a little bit of brainstorming. You're going to implement it. I want to see the implementation for each one of you. So you're going to draw this one and see what do you need to put inside or outside, what kind of circuits that you need to add to this so that it can work both ways. Now, if you are able to come partially with an idea, that means that now you're starting to really understand digital logic. You're going to have fun creating any other digital circuit. So try to exert some effort in brainstorming these are everything. This is everything you need. You need some inverters, you need some multiplexers, and you need an adder. Okay, let's brainstorm and see how we're going to come up with an idea.
Yeah. I was just thinking.
And the size of the multiplexer, I gave it to you. It's only 2 by 1 because we only have addition and subtraction. So these are the only 2 that we need to think of. I want to see implementations, even if it looks silly, even if it looks crazy, I don't care. Just put an implementation. I want to walk by and see an implementation for each one of you, even if you're working together. Put your thoughts in paper. That's how it works.
whenever you're doing one, I mean, you should at least split it back. And they went off last week, the one that will be choose what it is there. So that will be that. And then this third is they're all and it's gonna go to the day or whatever you do that. But exactly that's true. That's what we're gonna follow on. That's a more. Yeah, it's split it up, like just straight letters, plus the then 2 months, then to your actual. So I can show expected to get these. And then I'll share one. Yeah, I think you change the scene. From the straight line, so much the much inside. Yes, that's all right. I think that's one difference. If we're doing it, we still are. I was starting at school, I got my clock.
So where is it gonna be? Which one is it gonna be the one? Is it gonna be the I love like,
So.
Okay, and your team, you said your team is gonna complete the months. Through which one?
Yes.
Okay. No, now you're, you want for everyone to be what you're going. Now I see you use the multiplication. Oh, okay, so you use the multiplier, but now you did two circuits, two complete separate circuits in one multiplier. No, that's not what I want. I want to put the multiplier to only compare between the two operations within the same, using only one of them. So you're getting close, but you don't need to rearrange your design a little bit. Like that design is gonna cost more money.
Can I show this example?
Yeah.
Does that make sense? So, I drew boxes to show they're all
Okay.
multiplexers, but, that first one we connect to the cylinder to those and have like the straight input and like the complement of it. It go down and each of the multiplexers would have the same one selecting.
Okay, so you're doing it for the A and the B?
Yeah, because I can give you either one negative.
No, it's always gonna be A plus B, A minus B.
Okay.
So the only B is the one that would change.
So same thing, ignore that, but then that side would be the same where they're all getting selected by that first one. Because if one, it's gonna switch it to the negative, which is.
So you're one here, but what is the relation between, oh, sorry, what's the relation between the one here and the rest?
If there's a one there, that means it's two common, right?
No. It's just a number, it's
Okay.
part of the number, yeah, but you are getting close that you're using the multiplexer to either get the complement or the number itself, so there's something close there.
I see.
So Andrew, can you come up? Okay, so on the board. Yeah.
I feel like I know them.
So you have colors if you want to use colors. Okay, let's pay attention here. Let's see how, we only want, these are the tools that I gave you. You only use one of this. Okay, you can't use more. Because if I use more, let me just do one for the adder, one for the subtractor, I'm done. Okay, but I want to have only one thing that can, you know, work both ways. So the ones he's writing down here, these are the multiplexers. And these are like the selectors. He's gonna take all the selectors to go to the C input. We'll have to explain to us why. Now, the two inputs of the multiplexer, you chose one of them is going to be connected to an inverter. The other one is just to the B directly. So one of them is connected to the B, the other is to the B complement. So like this is your two inputs. One of them is B, and this is the B complement. Okay. And he connected the selector to the C input. So that's going to be your B3, B2. It can be B3 or B complement. I don't know. Okay, put your A's. So I have my 4 A's because we're always doing A plus B or A minus B. Okay, good. And of course, you have the outputs, which is the C output and C3, S3, S2, S1, S0. Now, you need to explain what you've done.
So, because this is the A's, they don't have the.
Anything to happen to them?
This is gonna be the deciding factor of plus or minus.
Excellent. So the
And
carry input is your decision. Do I want to do addition or subtraction? Okay, good.
up here, this is gonna be the B3 original inputs.
Uh-huh.
And depending on what you want for subtraction or addition, this will change your selection. So technically, this would be.
The 0. Yeah, you can just say 0, 1. 0 and 1. Yeah. So it's telling you that when the selector is 0, I'm choosing all the wires that are connected directly to the B. When my selector is a 1, I'm picking or choosing all the B's complement. And because the C input is a 1, that one is going to be added. So it's going to do the subtraction for me. Excellent. Thank you so much. Probably you did it much better than what I did here. So we had this big thing here. This is my adder. And what I want to do is the B3, B2, B1, B0, the A's are just going to be the same. They don't change. So what I need to do here is that like he just put it outside. I just, so that you understand what I did. I just put it in box. And inside here, we're going to put multiplexers. Okay, this is the first multiplexer, second and third and fourth. It's going to have two inputs. One of them is to the complement. The other one is to the wire itself. And the selectors, the red ones these are all the selectors. All the selectors here have to be connected to the same selector, right? I cannot take this one to something and the other. If I want them all to work synchronously together, I have to connect them all to the same input. So here, let me just do this. So you're going to have these two connected to the B3. These two are connected to the B2, to the B1, to the B0. And all your selectors are going to be connected to the C input. Just, okay, all of them are connected to the C input. Now, how does this work? Okay, if I say A plus B, let's do this. If I say A plus B, we said that for the selector C input, if I choose C input to be 0, so that means that you have a switch there on your FPGA board. You're going to make that switch 0. If you make the switch 0, you know that the two numbers you're putting in there, an addition operation is going to happen between them. Okay. If you make the switch go to 1, you know that the two numbers you put there, the operation that's going to happen between them is going to be a subtraction operation. So I choose my C input to be 0. So it means that this is 0, 1. So it's going to select the B0 to pass through, the B1, the B2, the B3. Then I'm just going to add the A to the B. Simple. Now, if I choose my C input to be 1, it means that I will be choosing B0 complement, B1 complement, B2 complement, B3 complement, and then I will be adding a 1 to it because that C input is already a 1. Okay, and we said that the definition of the 2's complement is that I have the A, I switch the minus to positive, and then I put the B complement plus 1. So I did put the B complement and I added a 1. Now the performance, what's going to happen is that it's going to perform a subtraction operation. Excellent job. Okay, so this is one of the circuits in your microprocessor. Of course, it's not that easy. We have multiplication and division, but we're not going to go through it. Why? Multiplication and division is all going to pull down to addition. Because multiplication is addition, division is subtraction, and subtraction, I can take it back to addition. Okay, so even as long as I know how to create my adder, I can add a subtractor, I can add a multiplier or a divider. Okay, a division to do the division operation. Okay, so this is beyond the scope. We just learned the adder and the subtractor. Now, also what you're going to find in your microprocessors, and it exists in your phones and like anything that is digital. We all have WhatsApp, right? Oh, you don't have WhatsApp? Okay. So some of you have WhatsApp. So one of the most important designs, we're going to talk next time the details about that design, the encoder and the decoder. Okay, so we have two systems. One is called encoder, the other is a decoder. So for example, you're typing on your phone, hello world, for example. Okay. What happened is that your microprocessor in the phone is just going to take it and encrypt it. So it's just going to look like this, something that you don't understand, your computer does. Okay, and then it will go to the receiver side, and then I will decrypt it. So it's like I'm giving it a code, encoding it, and then I will decode it so that it can come to you in a way that you understand. So we're going to learn about how can I do encoding and decoding. We're going to go through all the mathematical description of encoder and decoders. How do they work? But the basic idea is that for the encoder is that I take our language and you put it into the computer language. So it means that you take the data, you convert it to code. Okay, it's like your name is Dan, but I'm going to give you a code of 111. Okay, so when I say 111, we understand that that's Dan, for example. So that's how I transfer what our language is to a code. And now in the decoder, I take the code and then give it back to the data, the original data that I was sending. Okay, and that is the same thing for any microprocessor. You're typing on your keyboard, all the letters. Remember, what are the codes that we've learned about in the computer? We learned about two codes, one of them for English, one of them for all the languages of the world.
ASCII.
The ASCII code and the Unicode, okay? So this is exactly what happened. The ASCII code and the Unicode, for them to perform, they have to have an encoder there. I have to have an encoder in my computer. So that when I hit the letter W, it will encode it using ASCII code or Unicode. It goes through the microprocessor, whatever you want to do with it, and then it will decode it so that on your screen, you can see the letter W again. Okay, you're not going to see all the hidden codes there. Okay. So we're going to learn how we build those two circuits next time. Now, what kind of questions do you want to ask for today? Huh? Yes. Next exam? Don't worry, it's going to take some time. I know that the first two were so close. By the way, the lab is not going to be here starting from next lab. We're going to go downstairs into a real lab. Okay, you're still going to be using computers, but the other class are going to be using the devices that we have there. Okay, this week, yes, starting from this week and all the way to the end of the semester. Labs are going to be downstairs. I will send you the room number. No, we are not done yet. Any questions first? So just to wrap up, we've learned about half adder, full adder, that's going to be in your pre-lab, How can I create the half adder, full adder? How can I find the relationship between both? How can I create a 4-bit full adder? How can I create a subtractor? How can I combine them in one circuit by using some multiplexers and some inverters? Yes, Jay.
I don't think you can the audio principle.
No. It's connected to my laptop, not to this one.
Okay, so I just saw on the bottom left corner. It says-
That's always there because this
Okay.
one is not connected to it. Don't worry. The voice is gonna be there.
Okay, good.
Yeah, we do it like that. It's I mute it from this computer and it's on my laptop.
Okay.
Any other questions? Okay, so see you on Thursday.